Beta unsaturated carbonyls are an important reactant in many reactions. These are interesting compounds since they can undergo two types of additions with nucleophiles. For example, nucleophiles can add to alpha beta unsaturated carbonyls by attacking the carbon of the carbonyl, producing this tetrahedral intermediate, which are then protonated to become a product that you see here. This is what we refer to as a direct or a 1,2 addition. This reaction is actually what we saw in the last few sections with nucleophiles adding to carbonyls of aldehydes and ketones. Now, if you have an alpha beta unsaturated carbonyl, an additional reaction besides direct addition to the carbonyl is addition to the beta carbon of the alpha beta unsaturated carbonyl. In case you're unfamiliar with the terminology, alpha beta unsaturated carbonyls are compounds like these that contain a site of unsaturation between the alpha carbon, which is the carbon next to the carbonyl, and the beta carbon, which is the next carbon over. This double bond here, as well as the carbonyl, have two sites that are electrophilic. In other words, two sites where a nucleophile can add. The nucleophile can add to the beta carbon, or it can add directly to the carbonyl carbon. Adding directly to the carbonyl carbon, again, is called direct or 1,2 addition. Adding to the beta carbon is called conjugate or 1,4 addition. When a nucleophile attacks the beta carbon, the product that we obtain will look like this initially. So there will be a negative charge on the oxygen, which can be protonated to produce essentially, or at the end, this saturated aldehyde or ketone. Perhaps an easier way to visualize this is using this other resonance form, which is an enolate. We'll talk about those later. Enolates will be protonated and produce the saturated aldehyde or ketone. Going back to this intermediate, the way you can think about this reaction is we have here an enolate, a resonance form of the enolate. If that gets protonated, the result, if you imagine adding a hydrogen here, would be an enol. And as we learn, enols are easily converted through tautomerization into carbonyls. Strong nucleophiles like Grignards and organolithiums will add irreversibly to the carbonyl of an alpha-beta unsaturated carbonyl, such as the one shown here. In this example, the ethyl group will be transferred to the carbonyl carbon and give you a tertiary alcohol with an extra ethyl group. Now, this addition is considered a direct or a 1,2 addition, and it typically gives you the fastest forming product. So, in other words, adding this ethyl group to the carbonyl is faster than adding it to the beta carbon. And so, as a result, we get what we call the kinetic product. In other words, the product that forms the fastest. And another example of a very strong nucleophile that would add irreversibly and will add to the carbonyl carbon of an alpha beta unsaturated carbonyl would be lithium aluminum hydride. So this is a reagent that produces hydrides, and that hydrogen will add to this carbon, turning the ketone into an alcohol. Moderate nucleophiles generally will do a reversible addition to both the carbonyl carbon as well as the beta carbon. And at the end of the reaction, the product that we typically obtain is the one that results from 1,4 addition. In other words, adding to the beta carbon. So in this example, using a thiol, which would be considered a moderate nucleophile, at least in relationship to Grignards and hydrides, the sulfur will add to both the carbonyl carbon and to the beta carbon, And at the end of the reaction, the most stable product, what we call the thermodynamic product, will be the product that we get from the reaction. So that is true for any reversible reaction. So in this example, the sulfur, the thiol, will add to the beta carbon, eventually getting rid of this double bond after the addition of a hydrogen to the alpha carbon. And so in the product, we will have a sulfide substituent added to the beta carbon. The double bond will be gone and the carbonyl still intact. Another moderate nucleophile is the cyanide ion that generally adds to the beta carbon. And cuprates or Gilman reagents will also add an alkyl group to the beta carbon. So these are the cuprates, that is, are examples of carbanions, but unlike Grignards and organolithiums, they're considered more moderate nucleophiles, and so they generally add to the beta carbon. Note that although I'm showing examples here with ketones, alpha-beta unsaturated ketones, the reaction works the same whether we use an alpha-beta unsaturated ketone or an aldehyde or ester or amide or other similar carbonyl compounds. One last point here, the reason why the addition occurs at the beta carbon due to this reversible reaction is because a carbon-carbon bond is a weaker bond than a carbon-oxygen double bond. And so when we have reversible conditions, getting rid of the double bond is favorable due to the fact that we're getting rid of a weaker bond compared to a stronger bond. Under kinetic conditions, which is what we saw in the previous slide with strong nucleophiles, the addition just happens through a mechanism that is the fastest mechanism, which is the addition of the carbonyl carbon. So in that case, the reaction wasn't reversible, so we only get the addition that occurs the fastest, which is the addition of a nucleophile, strong nucleophile, to the carbonyl carbon. Mentioned before, Grignards and organolithiums are much stronger nucleophiles than the milder cuprates. So cuprates generally will do an addition that is reversible to the beta carbon. So it will result in this product. And Grignards and organolithiums will add irreversibly to the carbonyl carbon and produce the kinetic product. So it is the one shown here. Notice the double bond is intact in the direct addition, while in the conjugate addition, which is what we get with cuprates, we get an addition to the beta carbon, and the carbonyl is the one that is intact. Isocitrate is a molecule that is biosynthesized through a conjugate addition of water. So it starts off with this alpha-beta unsaturated carboxylate. So here we have the conjugate base of a carboxylic acid, which we call a carboxylate. And there's an alpha-beta double bond here. Through this enzyme shown here, water will be added to the beta carbon and result in isocitrate, which has an alcohol. There are several anti-cancer drugs that contain an alpha-beta unsaturated carbonyl of some sort. For example, this anti-cancer drug shown here, vernolopin, has an alpha-beta unsaturated double bond that is next to this lactone or cyclic ester. These compounds are able to stop cancer by the fact that DNA polymerase contains a thiol group, which is a key nucleophile or a key enzyme in the polymerization of DNA, and therefore is very important in the spread of cancer or the replication of cancer cells. However, if we throw in an anti-cancer drug such as this one here, that thiol group will add to the beta carbon of this beta unsaturated carbonyl and be linked to it and therefore be inactive. So DNA polymerase will no longer be able to help cancer cells replicate. There are a few more examples shown here of other alpha-beta unsaturated carbonyl drugs that are anti-cancerous for the same or through the same mechanism. So we can see here an alpha-beta unsaturated carbonyl highlighted also here in blue. And then here we have a highlighted alpha-beta unsaturated ketone. In this question, we want to predict which lithium diorganocopper reagent or which Gilman reagent we want to use, as well as which alpha-beta unsaturated carbonyl we want to use in order to synthesize these two compounds that you see here. As a reminder, lithium diorganocuprates or copper reagents are compounds that add reversibly to the beta carbon. And so when looking at the two products that we have in this question, so here is the first one. We have a ketone, and at the beta carbon, so if you count, this is carbon 1, this is carbon 2, this is the beta carbon. We're adding, or it looks like we're adding this substituent here. So if you imagine putting together a lithium copper reagent that has the same alkyl group twice, so a CH2 bonded to a CH2 as shown here. We have now the copper reagent, or the Gilman reagent we need to do this reaction. And then we need to turn the ketone in the product into a double bond between the alpha and beta carbon. So using this ketone, this alpha beta unsaturated ketone, and this cuprate, we can make the product that is part of the question. In the other example, we started with this compound, and using a Gilman reagent, again, we will be doing an addition to the beta carbon of the ketone. So if this is the ketone, this is the alpha position, this is the beta position, we want to add this propyl group. So our Gilman reagent will have lithium with two ethyl groups attached to copper. And then we would be adding that to an alpha beta unsaturated carbonyl. So alpha beta position has a double bond, and that is next to this ketone.